So basically what I have shown is that, well, if this strategy works, then we should be able to get something like this. Probability tau x greater than m behaves like kappa, expectation of u, x plus s mu m, tau x greater than mu m, divided by m to the power p over 2. Okay, so that's what we should be able to get. Now, if you look at this expression, so here mu m is going to be a stopping time. Then basically, so we have this order in the denominator n to the power p over 2, which is the same as for the Brownian motion. Now, if you look at the numerator, then if we manage to show that this converges to a constant, then somehow it will give our required asymptotic. Okay, so if we manage to show that, well, here we really need the limit for the stopping time, but it will be sufficient to show it for deterministic time. If we manage to show that lim m goes to plus infinity, expectation u x plus sm, tau x greater than m exists. Okay, so if we show that this limit exists for each x, long x belonging to k, so we can call it v of x, then it should give us the answer, right? So then one can expect that probability that tau x greater than m behaves like kappa v of x divided by m to the power p over 2 as m goes to b. So let's define what v of x is. So v of x is this limit, if it exists. Okay, so basically, as you can see now, we have somehow a similar procedure. So in one-dimensional case, somehow first we try to prove that expectation of the overshoot is finite, and then we derive the asymptotics. So here we're going to split our approach into steps as well. So step 1, that's the approach is. So step 1, prove that v of x exists and importantly belongs to 0 plus infinity. Okay, so we want it to be finite, of course, because otherwise it's just useless information. V of x is 0 is in certain sense it's okay, but again, this means that it's not precise. Okay, and step 2, use the strategy above to transfer the results from BM to random box. So we'll try to do as much as possible, but I'm not sure if I'm able to cover everything today, so you can always refer to this paper. Maybe I will give another lecture if there is some interest, we'll see. Okay, so that's what we can do now. Before moving on, let's just compare this kind of discussions. So far it's some kind of vague discussion. Let's see what it means in one-dimensional case. Okay, so let's get back to one-dimensional case, just to understand the connection with the one-dimensional case. So one-dimensional case. So let's write down what asymptotics are in one-dimensional case. Probability that tau x Brownian motion greater than t is behaving like square root of 2 over pi x divided by square root of t when t goes to plus infinity, x is fixed. Okay, so that's the one-dimensional case situation. So we can see that.
And that's for Hessing the negative half-line.
Yes. So you start Brownian motion at point x, which is in the positive half-line, and you wait until it hits the negative half-line. So that's the asymptotics. Okay, again, there is an explicit expression, and you can work this out from the explicit expression, these asymptotics. And u of x. So if we look at this expression, we can identify u of x. U of x is just x. Okay, and well, it's clearly a harmonic function because if you differentiate it 2 times, you're going to get 0, and also when you plug in dt instead of x, you're going to get Brownian motion, which is a martingale. Okay, so that's clearly a harmonic function. Now, if you look at this limit, so lim expectation, so the limit on that word. So lim u x plus sn tau x less or equal than n. So in this case, u is just the identity function, lim n goes to plus infinity, expectation x plus Sn tau x less or equal than n.
Not less than or equal to or greater than?
Tau x greater than n. Yes. It will be well, it will be less or equal, but I will do it later. Okay, so that's what we want to find, just to connect it to one-dimensional case. So if these guesses work, E is correct. So what we can do, we can write firstly this expectation as difference of 2 expectations, expectation x plus Sn minus expectation x plus Sn tau x less or equal than n. Okay, so that's the first step of the procedure. Now, if you look at this expression, well, you can calculate it immediately or use the fact that x plus Sn is martingale, whatever you like, but it's x. Right? So the first one is just x. Now, for the second one, you can apply the optional sloping theorem. X plus Sn is the martingale, and the optional sloping theorem is going to give you expectation x plus S tau x less or equal to 1. So that's by optional sloping theorem. So that's going to be x minus expectation and lim and goes to plus infinity, expectation x plus S tau x less or equal than n. Now basically if you show that this expectation of S tau x is finite, and that was step 1 in one-dimensional case, Then you can apply the dominated convergence theorem, which will tell you that this is exactly expectation of x plus s down x. But of course, the main thing is to show that indeed this expectation is finite. And as a result, you're gonna get a minus expectation of s tau x, and that was exactly, well, up to a constant function v of x, which we found in one-dimensional case. It was, I think in one-dimensional case it was divided by something else, but doesn't really matter. So all functions are defined out. All harmonic function was. Okay, so that's more or less. As you can see, somehow this limit, in some sense, is, at least in one-dimensional case, is equivalent to the analysis of the mean of the overshoot. And in multi-dimensional case, in certain sense, it will be equivalent to this as well. Okay, so.
And you're going to tell us what you mean by overshoot when you're in a tone.
Well, overshoot.
You don't have to do it now, just.
Well, why not? So I will not have that time, right? So basically, what happens is that we are not going to look precisely at the mean of the overshoot. So we're going to look at the mean of some function of the overshoot. So in one-dimensional case, this was exactly mean overshoot. So what's the meaning of the overshoot? So basically, that's the difference. So when your random walk moves inside the cone, as soon as it leaves the cone, it doesn't really hit the boundary. So basically, vaguely you can define, well, overshoot as this difference, right?
Okay, so it's a vertical.
Well, yeah, so here it's not, somehow it's not really useful to discuss that kind of definition. So what I mean is that there's always some kind of overshoot. So as soon as you exit the cone, you are not going to be at the boundary of the cone, you're going to be outside of the cone. This means you have an overshoot. So you can specify a quantity if you wish, but we're going to be looking at some function of this thing. So we don't really need anything more precise than this. Okay, so effectively that was one-dimensional case. Now we can try to use the same strategy in the multi-dimensional case, but we are going to have a small problem. Okay, so I'm going to erase. So we can try to use the same strategy in multi-dimensional case. Okay, so then if we try to use the same strategy, what it means is that we can write down expectation ux plus sn, now x greater than n. So I can try to do exactly the same thing. So I can write this down as expectation of ux plus n, sen minus expectation of ux plus sn, tau x less or equal than n, and then try to do something about these expressions. If I want to prove that the limit exists, very similarly to one-dimensional case. Now here we come across a problem. In one-dimensional case, ux plus Sn was just x plus Sn, and it was a martingale. So in one-dimensional case, you can immediately conclude that this is equal to x, and that's it. So in multidimensional case, we don't know what to do, because nobody guarantees that u of x plus Sn is a martingale. Okay, so basically, so that's one of the problems. So this is something not very good, but on the positive side, so if you look at this u of x plus Sn, so it's not a martingale, but ux plus bt is a martingale, right? So if you plug in Brownian motion instead of the random walk, you're going to get a martingale as well. So this means that in some sense, this u of x plus Sn should behave like a martingale. So it should be close to a martingale. So basically, it's not necessary that u x plus x, expectation of ux plus x1 is equal to u of x. But what might happen is that if you take a difference, then this might be small, sufficiently small, and then somehow you can control this difference. And this does happen, in fact, and that's what we are using. Okay, so let me do this more formally now. So basically, to use the same kind of technique, I need to deal with this difference, and for that I'm gonna change my function u of x a little bit. Okay, so I don't need maybe it's better to say existence and finiteness of v of x, because that's what we're discussing. Okay, so for that, what I'm gonna do, I will define a new function v of x as follows. So v of x is gonna be equal to u of x when x belongs to G. So G is a domain which will be slightly bigger than the original form, and modulus x to the power p minus a when x does not belong to G. Okay, and let me write down what G is. So where G is K union with x that which are not from my cone, but the distance to the cone is less or equal than modulus x to the power of 1 minus a. So here, okay, so don't need this apparently. So here a is going to be small.
Couldn't you just say it's the set of points that are distance less than or equal to x, so 1 minus a from k?
Distance, set of points with distance from
whose distance is less than or equal to that from k.
Yeah, I guess you should be able to say this. Okay. But in any case, it should include the cone and a slightly larger set. So effectively, so u of x will be, so my new function v of x will be equal to u of x in the cone and a little bit outside of the column, and to some new function model x p minus a everywhere. Okay, and then what we can do, we can define a narrow function, then let f of x to be equal to expectation e x plus x minus e of x. Okay, so this is the arrow in one step. So if b was a martingale, this would be equal to 0. In general, without a martingale, I have to work with this arrow. So this is the summary function. Okay, now I can define an auxiliary martingale. So then, sequence yn can be defined as follows. So y0 is equal to b of x, and yn plus 1 is equal to b of x plus s plus 1 minus the sum from 0 to n f x plus sk. Okay, so you define a new sequence. So what we are doing, we're just taking b of x plus sn plus 1, then we're subtracting all those errors, and as a result, you're going to get a martingale. Okay? So then, so lemma 2.1, yn is a martingale. So although original sequence was not a martingale, we have modified it and then we get a martingale. So the proof is just 2 lines. So first of all, integrability follows from our conditions. Integrability of yn plus 1, and then if we just consider a difference of 2 terms, expectation yn plus 1 minus yn given fn, that's proof. Then this is equal to, so basically what happens is that this term will remain bx plus sn plus 1 minus bx plus sn. So most of the terms will be cancelled here, and only the last one will stay, fx plus sn given fn. Okay, now minus fx plus sn can be taken outside because it is fn measurable. And when you look at this difference, expectation vx plus sn plus 1 minus vx plus sn, then basically by definition of given FM, by definition of f, that's just going to be fx. That's going to be 0. Okay, so that's well, it's kind of clear. So just taking y and subtracting all the differences are possible in the math. Now basically, because of that, we can now using this representation, using lemma 2.1, we can write. So now we have a generalization of the representation which I had in one-dimensional case, but now it's gonna be more complicated. Right? So expectation of ux plus Sn on the event tau x greater than n. Well, on this event we are inside the cone, so u is equal to v. So that's gonna be expectation v x plus Sn tau x greater than n. Okay, so that's one thing. Now what I'm gonna do, I will just copy the expression on that blackboard, so I can express my v as yn plus 1 plus these errors. So that's gonna be expectation yn plus the sum from 0 to n minus 1 fx plus scale on the event tau x greater.
Can you specify this the filters you used in FNV?
Fn is the filtration to the is the natural filtration of the random walk.
Do we also need to include the capital X there?
Well, x is fixed in the beginning, so I just fixed.
You fix.
X is fixed, yes. So
Capital X.
It's not capital.
That's a little x.
It's
little x. So
That's little X. Then
Yeah.
we have the little X there, right? Are they same? I thought you defined f little X with V and little X plus capital X. So that's what we defined for the fx. You have capital X in here.
yes.
So did you use the capital X in here?
It's typo. It's small x.
So every x in here is a little x.
The second line
Yeah,
is
every x is here is little x. So what happens here is that x plus Sn is some kind of fixed number in this filtration. And you have x plus Sn plus capital X here. Right?
yeah. So everywhere else, if when you see capital X,
Yes.
okay, this is just optical issue. It's actually small.
That's my handwriting.
That's his handwriting.
Let's be honest.
Even if x is greater than capital S, it's still small x. Okay.
No. He used this capital X to define this.
Yeah, I
little
understand.
X.
Yeah, but still on that.
Yeah,
on that
And
one,
that one is small.
yeah, it's optical
On the
illusion.
Well, let's try definition immediately.
Yeah.
So fx is expectation of v x plus x1
Yeah, this is better.
minus v
But
x.
still, because you use curly x
Yes,
on the top.
I forgot about
Now we know.
curly x.
Now we know. Now we know.
Now I'm confused.
No, I'm confused.
Isn't there only one capital X on here, and there should be 3 little x's?
It's all small x. It's all small x.
Okay.
Okay.
X1.
No, I'm with
It's all small
you.
So Mark, the problem is maybe you're not You're not teaching on a regular basis here. Otherwise, you would be used to our students' handwriting.
But the next X is also a little X.
Yes. Yes. Yes.
It's a clear X.
But for us, it is obvious, Mark, because our students always
No,
write.
I mean, that's what I was thinking, but since it's confused Ava anyway.
Yeah. Sorry about this. Yeah.
Okay, let's okay, so that's what we have now. Now let's do the same trick now. And we can do it because we have a martingale. Right. So first of all, I will get rid of this sum. I will write it separately, and here I will get expectation of yn minus expectation of yn on the event tau x less or equal than m. Okay, so I immediately change this, plus this summation, expectation, sum k changes from 0 to n minus 1, f x plus s k tau x greater than n. Okay, now I'm using exactly the same reasoning in this line, so I'm going to apply optional swapping theorem. Well, here it gives me expectation of y0, which is v of x, and because x was inside the column, that's just u of x. Now, with this term, I'm going to get expectation of y tau x on the event tau x less or equal than n, plus expectation, the sum, k changes from 0 to n minus 1, f x plus s k tau x greater than n. And okay, so here again I'm gonna use this expression one more time, and I can write down y of x using this sum, which will give me just u of x. Here I will have expectation v x plus s tau of x on the event tau of x less or equal than n.
So things now I'm confused. Once again, why is it u of x replacing expected value of yn?
Well, here it's not replacing, so y tau of x, I'm going to use the definition of y. So I'm going to write y tau of x as v x.
No, in the previous line.
Here.
On the left, behind your hand, u of x, underneath now, just this one.
This one.
Yeah, I understand the second term because you said it's OST, but why is it u of x?
Well, here that should be v of x, but v of x is equal to u of x inside the
Why
code.
should it be v of x?
Well, v of x is in
Because it's a martingale.
yeah, it's a martingale. So yn is a
No,
martingale.
okay. Yep.
So it's a martingale, that's why
Yep.
you have u of x here, and that's why you have y of tau x there. Now you just get back to y tau of x, you copy this bit. So have minus here, so you have the sum, expectation, k changes from 0 to tau x minus 1, f x plus s k. tau x lesser or equal than 1 plus plus this sum, so that's expectation. The sum k changing from 0 to m minus 1 f x plus s k on the event tau x greater than m. Okay, so that's a very long expression. And let me just summarize what we've got. So here we have exactly the same term as in one-dimensional case. Now this term is an analog of the corresponding term in one-dimensional case as well. In one-dimensional case it was just x plus s tau x. We have here some function d of x plus s tau x. And now we have two terms which appear because of the martingale error. Okay, so these two terms. Okay, so basically it's not as bad as it looks like, and it can be analyzed, and for that you need two auxiliary results. So to finish the argument, we need we need, first of all, lemma 2.2, and that's the one that we did not prove in the paper as well. So this lemma belongs to McConnell. It was proved in 1984. Here the lemma says for every beta less than p, we have first of all expectation of tau x to the power beta over 2 is less or equal than c 1 plus modulus x to the power beta, and second of all expectation of m of tau x to the power beta is less or equal than c1 plus modulus x to the power beta, where m tau x is just the maximum, k less or equal than tau x modulus x plus s k. So I don't really want to prove this lemma, but well, in principle that's something that you can prove using the Lyapunov function. You can construct a Lyapunov function and analyze it to prove this lemma. Now,
sorry, this is for cones, right?
Huh?
That's for cones.
That's for cones. Exactly the same setting, exactly the same tau x, exactly the same thing. So we know that all moments of tau of x, which are less than beta over 2, exist if beta is less than p. That's something that you can expect from the answer. So that's one lemma that we need in order to finish this argument. And the second lemma, 2.3, says let the moment and normalization assumptions hold. Then, for some delta greater than 0, and some c greater than 0, modulus f of x. Here f of x is my error function, and it is less or equal than c times modulus x to the power of e minus 2 minus delta, when x belongs to the cone and modulus x is greater or equal than 1 and less than a constant when x belongs to the cone modulus x is less than 1. Well, somehow, of course, nobody will say that this construction will work if we take some kind of arbitrary function u and v and try to perform it. So the point here is that the error function that we getting using this construction, the error function is sufficiently small. So that's the main point why we made such a choice of these functions. Now, suppose we know these lemmas. And now I think I can finish this argument in about 5-10 minutes. So first of all, so I want to prove that this limit exists. Okay, so I'm going to keep just the last line. So first of all, we made a choice of function v, and this choice was the following. So then my choice of v. So what happens is that outside of the cone v of x is less or equal than c modulus x b minus a. Okay, so that's how function v was chosen for x that does not belong to k. So that's how this function was chosen, and then what we can see is that here then we can apply the dominated convergence theorem. Since b s tau of x is less or equal than c modulus s tau of x to the power of b of a, which is integrable by lemma we will obtain expectation bx plus s tau x less or equal than n will converge to expectation of b x plus s tau of x. Okay. How much time do I have?
No, because then perhaps you said 5 minutes, 10 minutes, so I think it's
Okay,
okay
so
if you keep going.
That sorts out this term. Well, so basically, then using, so I'm not giving the details, but using the further inequality, we can show that. So the next thing that we can show is that expectation of modulus k changes from 0 to tau x minus 1 modulus f x plus s k. Well, I'll give you an intermediate step. So first of all, without any kind of further inequality, this is less or equal than expectation. You're just replacing this term by the maximum. So expectation of tau x m maximum modulus f x plus s k less or equal than tau x, and then you just use them at 2.3. You can replace this by modulus x plus s to the power of k, p minus 2 minus delta, and then you can replace x plus sk by the maximum. Okay, so you can say that this is less or equal than c expectation tau x and tau x p minus 2 minus delta, and then here you apply further inequality with appropriate constants to get c1 plus modulus x p minus delta. Okay, so the point is that this expectation is finite. So now I can erase this bit. So this expectation is finite. Then, because it is finite, you can see that this term, again, converges. You can apply the dominated convergence theorem for that. The third term converges to expectation k changes from 0 tau x minus 1 f x plus s k. Okay, and this expectation is finite, which is finite. And the last term and the fourth term converges to...
You can switch to a better market perhaps.
Zero.
Sorry.
And the fourth term converges to 0. Again, bidominated converges here. Dominated convergence. Okay, so as a result, v of x is finite. So that's lim and goes to plus infinity. Expectation ux plus sn. Tau x greater than n. So this is finite, and I can write down an expression that's going to be u of x minus expectation of v x plus s tau x, and plus expectation, the sum of error terms. K changes from 0 to tau x minus 1, f x plus sk. Okay, so I can now so then, basically what we have, so we have v of x, this is finite. Now some not very difficult additional arguments will show that v of x is greater than 0, well at least for some values of x. And another thing is that this is a harmonic function, that's one more argument. Okay, and somehow once we finish this, well, of course, I haven't proved those two lemmas. So once we have it, somehow this is the first part of the proof. So somehow this shows that function v of x exists. This function v of x is harmonic. Now the second part is basically somehow to make use of this and to use the universality. But well, I don't really have time today for the second part, so I will leave it for you as a homework. Do another lecture. Okay, so that's it probably.
Okay, so let's thank our speaker.